What's going on, everybody? Mr. Gustin back in the physics classroom. I want to talk to you today about a review problem we're doing. There's a review problem on my slides where I've got a scenario like this. And it's actually I've got the marker for it, so I'll do it. There's a red block sliding down this incline, and it's a frictionless incline. It goes across a frictionless table, and eventually it collides with this blue block right here. Now, both blocks are initially at rest. The red block has a mass of 2 kilograms. The blue block has a mass of 1 kilogram, and then both of them launch off the table. You can see kind of both paths. This is 8 meters high. The initial position is. The position at the tabletop is 6 meters high. We find out in the problem that the red block ends up traveling 2 meters before it, I can get the cap off, before it hits the ground. All right, so it lands here 2 meters away from the base of the table. And you're asked a series of questions on my slide. So A asks how fast is the red block moving before the collision. B asks how fast is it moving after the collision. C says how fast is the blue block moving after the collision. And then finally, how far does the blue block land away from the base of the table. This is our goal. We want to end up figuring out how far away that blue block is from the end of the table. So the first thing we're going to do is kind of look at our picture here and say, like, what are the different things happening here? Well, I have the red block going from here to there, not losing any energy. There's not a collision, so I don't need to consider momentum too much. But I can easily say that UG from here equals the kinetic energy right down there as it begins to slide across the table. When the red block hits the blue block, I have to understand there's a collision. So I'm going to need to consider momentum right here, right before they leave the table. And then finally, afterwards, as these things go in this projectile motion, you know I'm going to have to use some kinematics over here to figure out what's going on after. So I've got 3 kind of sections to this, right? Anything happening previous to the collision, prior to the collision, is going to deal with conservation of energy. Anything happening right here in this instance when the red block contacts the blue block, that's going to be conservation of momentum. And then anything after the collision happens as these blocks go flying off the table, we're thinking kinematics. So let's go ahead and start with A. Question A asks, how fast is the red block moving just before it collides with the blue block? That sounds like energy. I'm going to go ahead and say UG before equals the kinetic energy right before the collision, right? As it slides down, it's gaining energy here. So I'm actually going to call it change in UG because I'm not using 0 at the ground. I'm going to use 0 right here. 0 is going to be right there for me. Just the 2 meter drop from 8 meters down to 6 meters. That's going to be my change in UG. So I'm going to go mg delta y is equal to 1/2 mv squared. I can do this math. We've been doing this math for a long time, so I know that those masses drop out. This is going to be a 2 meter change. This is 1/2 mv squared. I do my fancy algebra. I rearrange. I end up with the velocity being equal to 6.26 meters per second, right as that red block approaches the blue block. So no energy lost due to friction. This is a frictionless surface. Slides down, comes across, bam, 6.26 meters per second is that speed. Now, how fast is the red block moving right after the collision? That's question B. How fast, I'm going to call that V red after. We can call this V red before. We'll keep track of them that way because we know we're going to have to get into momentum at some point, so I want to make sure I have before and after speeds. So after speeds, I'm looking for the velocity of the red block afterward. Well, this is tough because the only thing I know about the red block afterward is that it falls 6 meters, which is a change in y, equal to 6 meters, and it moves horizontally 2 meters, which is a change in x, equal to 2 meters. This feels like kinematics, and we said that initially. We said after this projectile motion, kinematics. So let's go ahead and use some kinematics to solve this. Well, to figure out how far it traveled, to figure out how fast it's moving horizontally, I'm going to need to know how long it traveled, the time it traveled horizontally to cover 2 meters. I'm going to need to know time. So I'm going to go ahead and take this delta y and say delta y equals 1/2 gt squared. One of our basic kinematic equations for an accelerating object. And I'm going to go ahead and solve this out right now. So change in y is 6 meters. 1/2 g times t squared. I end up with t, once I do my algebra magic, t is 1.11 seconds. That's how long it takes for the red block to fall to the ground. Well, if it's going to fall for 1.11 seconds, it's also going to travel horizontally for 1.11 seconds. So I'll take this 2 meters right here and say, well, delta x is equal to the speed, in this case, the red block after the collision, times the time. What's that going to shake out to be? 2 meters is equal to v red after times the 1.11 seconds. I end up with, I believe, the velocity of the red block afterwards is 1.8 meters per second. There we go. Part B solved for. C says, how fast is the blue block moving? So I know all this about the red block before, the red block after, but how fast is the blue block moving right before the collision? I'm sorry, right after the collision. Let's find out. How fast is the blue block moving after the collision? Well, now we're talking about the collision. We're talking about this right here. And after the collision, I don't know how far it travels, so I can't rely on the same information I had here, right? I don't know how far it goes, but I do know that it's involved in a collision. So let's look at the conservation of momentum, because before we have the mass of the red block times the velocity of the red block before, and that momentum is the only thing that carries momentum in my red and blue block system. So then after the collision, we have mass of the red block times the mass of the red block after, plus the mass of the blue block and the velocity of the blue block after, which is really what we're trying to find right now. That's what we're going for. So I can start plugging some numbers in. This is 2 kilograms times the velocity before, which is 6.26 meters per second. Afterward, it's still 2 kilograms. I found out it's 1.8 meters per second, plus the blue block I know is 1 kilogram. And so I can find VB after just like that. I already have everything set up to find that for me. And I think I get something around 8, but let me double check. Yeah, I end up with 8.9. So my velocity of the blue block after the collision, once I solve my conservation of momentum, once I solve that problem for the after, right? I've got my before momentum right here. After the collision, I see that it's 8.9 meters per second. That's the speed of the blue block. Now I'm ready. I've got my horizontal speed of the blue block. I already solved earlier for how long it's going to fall for. I can easily go ahead and solve for D right now. D says, what is the change in horizontal position for the blue block after it collides with the red block? I know horizontally there's no acceleration, so I'm going to use this formula right here. Delta x is equal to 8.9 times, is that what I want to do? Delta x equals 8.9 times 1.1 seconds. I get delta x equals 9.879. I'm going to call that 9.9. 9.9 meters, roughly, is how far that blue block travels after it collides, or after the red block knocks it off of the table. And this kind of makes sense, folks, right? The lighter block travels faster after the collision. The heavier block travels slower. The heavier block's going to fall not quite as far. The lighter block will travel much further. This all kind of makes good sense to me. But again, the big takeaway is not so much the mathematical intricacies of it, right? The calculation stuff. The big takeaway is, look, we've got conservation of energy. We've got conservation of momentum, and we have kinematics. And can we, in our brains, can we fit those structures in there to know when to use an energy expression, when to rely on our kinematics and speeds and times, when to rely on our conservation of momentum, and when to rely on non-accelerating objects. These are giant ideas that we have covered all semester, and I'm hoping you're starting to piece these things together as we walk into our final exam and our last summative assessment. That's all I have for you now. Check your answers. Go watch this back. Review for your Unit 5 test, and I will see you in class tomorrow. See ya!